This webcast discusses Kepler's 3 laws of planetary motion. These laws were empirical in nature. Kepler found mathematical relationships which did an outstanding job of describing planetary motion. In fact, we still use them today very well. He did not really understand yet the reasons that planets move in this fashion. But he took data from Tycho Brahe and was able to derive correct physics equations, basically, to explain the motion of the planets. So his first law, found in the 1600s, is that planets move in elliptical orbits around the sun. And he determined that the sun is at one of the focus points of that elliptical orbit. So planets move in elliptical orbits. So it will be important for us to review some of the characteristics of an ellipse in order to be able to talk about planetary orbits. So in an ellipse, there are 2 axes. The axis across the widest portion of the ellipse is called the major axis, and the axis through the narrowest portion of the ellipse is called the minor axis. This would be the center of the ellipse, but the most important points of the ellipse are the 2 foci. If you draw a line between each of those focus points to the object that's moving around the ellipse, the distance from that object to both of the foci remains constant as the object moves in this elliptical path. So for planets in our solar system, the sun is at one of the focus points. So here would be a planet, and that red dashed line is the imaginary line from the center of the sun to the center of the planet. So one major characteristic is the semi-major axis. That is, it's half of the major axis, which is the axis across the widest part of the ellipse. And the semi-major axis is represented by the symbol A. Another important characteristic is the distance from the sun to each of the focus points. Here I'm showing it as the distance from the sun to the center of the ellipse. And that distance from the center to one of the focus points is called D. Okay, so sometimes the planet, as it moves around, reaches the furthest point in its orbit, the point where it is furthest away from the sun. That point is called the aphelion point. And at this point, the planet is moving at its slowest speed. This distance from the sun to the planet, when it is at aphelion, is called R max, because it's the maximum orbital distance. And that distance is also referred to as the aphelion distance, because it's the distance of the planet from the sun at aphelion. Now sometimes the planet is much closer to the sun. It's at what's called the perihelion point. And when the planet is at this closest point to the sun, it is moving at its fastest speed. This distance from the sun to the planet at perihelion is called r-min, the minimum orbital distance, and it's also referred to as the perihelion distance. So here is a figure that summarizes all of those important points in one figure. But again, so the planet moves around this elliptical path. When it is closest to the sun, it is at a point called perihelion, and that is where its speed is the fastest. And then it begins slowing down as it moves further away from the sun, when it reaches the very furthest point, which is called aphelion, it has its slowest speed in its orbit. The semi-major axis A is the distance from the center to the ellipse along the major axis, so it's 1/2 of the major axis. R min is the distance from the Sun to the perihelion point. R max is the distance from the Sun to the aphelion point. So elliptical orbits are commonly described by a couple of quantities. One is the semi-major axis, A. The other is something called the eccentricity. So let's first talk about the semi-major axis. So the semi-major axis is 1/2 of the width of the ellipse at its widest point. And you could also find A, it is the R min plus R max divided by 2. The R min and R max, when added together, equal the entire major axis of the ellipse. And so if you divide by 2, you get the semi-major axis. And then eccentricity is a measure of the elongation of an ellipse, or how much it deviates from being circular. The eccentricity is a dimensionless quantity, and it equals the ratio of the distance d to the semi-major axis. Remember that d is the distance from the center of the ellipse to each of the focus points. And so that ratio of d to a gives you the eccentricity. If the orbit were circular, the distance d would be 0 because the two focus points would both be at the center of the circle. And so therefore a circle has an eccentricity of 0. And as the eccentricity gets closer and closer to 1, which is its maximum value, the ellipse becomes wider and flatter, much more elongated. Okay, Kepler's second law deals with the speed of planets that are in an elliptical orbit. And he understood that the speed of the planet changes constantly as it moves through this elliptical path. It is moving fastest when it is closest to the Sun, and it is moving slowest when it is further from the Sun. So if you had an imaginary line drawn from the center of the planet to the center of the Sun, that line would sweep out the same area in equal periods of time. And this is called the law of areas. It means that an orbiting body sweeps out equal areas in equal amounts of time. In this figure, the time that it takes to go from position 1 to position 2 is the same amount of time that it takes to move from position 3 to position 4. And the sector of the ellipse, represented by the green area, 1, has the same amount of area as the sector represented by the turquoise area, 2. And then we get to Kepler's third law. In this law, Kepler found that a very important relationship, that the orbital period, which is the time that it takes for the planet to travel one full revolution around the Sun, is has a relationship to the semi-major axis. Basically, the square of the period is proportional to the cube of the semi-major axis. Notice that all of the quantity contained in the brackets is constant. 4 pi squared divided by the universal gravitational constant and divided by the big M, which is the mass of the central body, the mass of the body that the satellite is going around. Okay? And so the square of the period is proportional to the cube of the semi-major axis. This third law is sometimes called the law of harmonies. Unlike the first two laws, the third law is comparing the characteristics of motion of the various planets. and it found that the ratio of the squares of the periods to the cubes of the average distances, so that ratio, t squared over a cubed, is the same for every one of the planets. Let me go back here. Remember, I said that everything in that bracket, those brackets, is constant. And so that would be the same for every planet in our solar system. The quantity 4 pi squared over g, mass of the sun, would be the same for every planet. Let's go work a couple of problems that involve elliptical orbits. And so I'm going to go to our worksheet 7C, and let's look, please, at problem 3 in this worksheet. So you're talking about a comet here, and it's giving us a perihelion and distance and an aphelion distance. So, that's a big clue that this comet has an elliptical orbit. And they're asking the semi-major axis of the comet's orbit around the sun, and then I have added a question where I'd like to find the eccentricity of the orbit. But let's talk about A first. So they've given me the perihelion distance. That is r min. And so they're saying that r min is 0.35 astronomical units. And the aphelion distance is r max. And they're saying that that is 45 astronomical units. Well, I know that we talked about a relationship where the semi-major axis equals the sum of r min plus r max divided by 2. Because remember, r min and r max added together make up the entire major axis of the ellipse. And the semi-major axis is just half of that major axis. I'm just going to continue to work in the units of astronomical units in AU. I think that'll be okay. So I've got 0.35 is r min, 45 is r max, and so the semi-major axis here is going to be the 45.35 divided by 2, which is 22.675 astronomical units. Let's also find the eccentricity of this orbit. So the eccentricity equals the distance d. D represents the distance from the center of the ellipse to one of the focus points, divided by the semi-major axis. Well, I know that the semi-major axis equals the distance r min plus the distance d. And so I could solve for d here. D is going to equal a minus r min. And we found a, it's 22.675. They gave me r min, 0.35. So here the distance d is 22.325 AU. So now I'm in a position to find this eccentricity because I know d and I know the semi-major axis. And so we could just find that ratio and we'd get 0.985. So this is a very, long, flat elliptical orbit. It's very far from circular. Okay, let's also go down and do problem 6 together. So here we're talking about a comet, again, in an elliptical orbit. They're giving me the perihelion. So I know r min is 0.43 AU. And this time they're giving me A. The semi-major axis is 21.9 AU. And I have the mass of the comet, the mass of the sun, and also they're telling me that an astronomical unit, an AU, is this many meters. So the first thing they're asking for is the furthest distance that the comet travels from the sun. So that furthest distance, they're looking for r max. So I know that r max equals the semi-major axis plus that distance d from the center to the focus point. Okay, and let's see here. I think I can find d because I know the semi-major axis and I know r min. And r min plus d equals the semi-major axis. Okay? So I get 21.47 AU as d. So if I add that to the semi-major axis, then I'm going to have the R max. Let's see here. So semi-major axis is 21.9. D is very large itself, so that is 21.47. And so if I add those together, I get 43.37 AU is the maximum distance that this comet gets from the sun. Okay, then I'd like to find the period of the comet in years. Okay, so this is Kepler's third law, which says that the square of the period is proportional to the cube of the semi-major axis. So let's see, it's 4 pi squared over the universal gravitational constant and the big mass. And so let's see. So in this case, t squared is going to equal 4 pi squared over g. I have a decision to make of which mass to use. I have the mass of the comet, but I also have the mass of the sun. So the mass that I need is the mass of the central body, the bigger mass, which is 1.99 times 10 to the 30th kilograms. Okay? And then I need the semi-major axis. Uh-oh, I forgot the a cubed over here. I need the semi-major axis, but I need it in meters. And so I'm just going to convert that right here. So I've got 21.9 AU, but I need to convert that. 1 AU is 149.6 times 10 to the 9th meters. And that way I will have my semi-major axis in meters, and I need to cube the semi-major axis. Okay, so I'm going to do this math, and this is going to give me the period squared in seconds squared. So I've got 4 times pi squared divided by g, also divided by the 1.99 times 10 to the 30th, and then I'm multiplying that by the 21.9 AUs converted to meters raised to the third power. And so I get 1.046 times 10 to the 19th, but remember this is seconds squared. So the period, let me take the square root of that, is 323,410,395.7 seconds. The question is asking me for this period in years. Okay, so I just need to do a little conversion here. There are 3,600 seconds in 1 hour. There are 24 hours in 1 day. And I'm just going to use 365 days in 1 year. So let's see here. So I get 102.553 years.